So now that we've finished that brief review of probability, we're going to move on and talk about concept learning. So in this course, we want to use probability to reason about machine learning. So let's step back to start and think about what is the most general form of learning. So if we're trying to do any kind of learning, we want to define some kind of concept about the world. That is some hypothesis about how the world works. So we might write that as a given hypothesis, little h, out of all of the sets of the set of all hypotheses we could possibly imagine. So, for example, if we're doing uh, classification and we're trying to identify dogs, H is some theory about what a dog looks like in a photo. And if we're doing, for example, some kind of classification, for example, trying to identify dogs in photos, that hypothesis would be some theory about what a dog looks like in a photo, something that is probably brown with a nose and ears and whatnot. So to do that, we're going to make use of some data. So that is a big data set D, which is a bunch of observations that yi equals some particular value, small yi, for I 1 up to n. The notation I'm using here is a set. This is a set of observations I equals y small I colon for these particular values of I. So this, in principle, kind of encapsulates any kind of learning problem. So this could be a very specific supervised learning problem where, again, we're trying to come up with a model for what a dog looks like using where our observations are a specific photo of a dog combined with the specific observation that this is a dog or is not a dog. But it also generalizes to something like if I'm a child, growing up and learning what dogs look like, I'm going to have sort of very abstract observations. For example, my mom saying, "Oh, look at that cute doggy," or "Watch out, don't trip over the dog." And maybe not a lot of negative examples of my mom pointing to something and saying that is not a dog, but maybe some negative examples where if I say, "Oh, that's a cute dog," and mom says, "No, that's actually a cat and not a dog." So again, this could be kind of any set of observations about the world, and we're trying to learn some concept, some theory about how the world works. So let's start with an extremely simple example of this process. So let's imagine that there's some concept we're trying to learn from our teacher. And sort of the concept perhaps could be the powers of 2. So that concept is a set of numbers that follow the concept, and vice versa, all the other numbers don't follow that concept. And what we get is some set of numbers that do follow the concept, but probably not, we don't get a chance to observe all of them. And just for simplicity, let's say the numbers are between 1 and 100. So as a human, it's very intuitive to us that if we saw this list of numbers, 2, 8, 16, 64, that's probably a good idea that the concept is the powers of 2, because again, all these numbers are powers of 2, and it's sort of hard to imagine that we would get this set of numbers with the concept not being powers of 2. But if you think about it, it's a little bit tricky to figure out why this is a good concept, the powers of 2, because this concept here, the even numbers, equally well explains this set of observations here. Because again, all of these numbers, they are in fact even. Now you could do something simple, like you could say, okay, maybe I want uh, the smallest concept, that is the concept that has the fewest components that still explain all the values. Well, if I'm going to do that, why don't I just say that here, this is the concept here, 2, 8, 16, 64, and no other values, or equivalently, the powers of 2 except 32. Why do I think those are more intuitive concepts to match this set of numbers? Why do I think those are less intuitive than the powers of 2? So we can actually kind of get an experimental understanding of what humans do by doing an experiment like the number game on actual people. So the way the experiment works is the experimenter shows the person a number, which they say is in fact a member of the concept, and then asks them, what other numbers do you think are part of the concept? Now, so if, for example, we say just 16 is the member of the concept, well, people kind of aren't sure. So they know 16 itself, of course, is a member of the concept. And perhaps they think, okay, 16 is a power of 2. Well, I'm going to put a little bit higher probability on the other powers of 2. Or the people are more likely to report other powers of 2 as part of the number. People are also likely to say, well, numbers near 16, those might be part of the same concept. But of course, it's diffuse over this whole number line, so we don't really know. Same thing goes with 60. We could say kind of numbers near 60. But okay, so let's say we show people this again, powers of 2, 2, 16, 8, and 64. So again, they definitely put 64, 16, 8, and 2 in their concept, but you can see that people, almost all the people put 4 and 32. That is the powers of 2 that weren't given as part of the concept. So pretty much everyone said, okay, yeah, I think what's probably being depicted here are the powers of 2. And then you can see some other stuff going on, like maybe 6. If we think it's even numbers, 6 would be a reasonable thing to put in as well. You could do a similar thing. What if we show people numbers 16, 23, 19, and 20? Well, those are kind of all in the same range. So probably the concept is numbers in that range, like numbers that are close to 20. So you can see that people almost always said probably the numbers close to 20 are also part of the concept. So this is just giving us sort of like a practical view of how humans actually learn a concept like this. Okay, so we're going to try to formalize this process of concept learning that humans undergo. So to do that, we need to introduce a couple of concepts and define them. So the first one is called the likelihood. So we define the likelihood as the probability of data given a specific hypothesis. So note that this is redefining kind of a term that's used colloquially. So day to day, if we might use the word likelihood as a synonym for probability. I say, what's the likelihood that this coin will come up heads when I flip it? In probabilistic machine learning, we use the word likelihood for a very specific term, that is probability of data given a specific hypothesis. Which again, it is a probability, but it's a specific. We're using probability in a specific way. So what is the probability of an observed set of numbers in the number game given a specific hypothesis about which numbers are part of the concept? So let's try to write this out. Well, first thing, we imagine that each of our numbers is kind of independent, where we to get our numbers, we just grab numbers arbitrarily from our bag of numbers. So that is, we take the product over all the numbers we see, and we ask, what is the probability that we saw that number given a specific concept? And by the way, I'm not going to call this out for the whole course, but just the first few times I will note that we're using this overloaded notation where what we really mean is the probability that big yn, the random variable, equals this specific value, small yn. That's what we mean by just writing small yn in this probability. Okay, so we can keep writing out this likelihood. So again, we have this product over all of the numbers we see in our bag. Now there's kind of two possibilities. One possibility is that we see a number that isn't in the given hypothesis. So if that's the case, then the probability of this concept, this hypothesis, is zero, obviously, because we're not allowed to ever see a number that's not part of our concept. So I'm writing this like this. This I with the two bars is the indicator function. The indicator function looks at a logical expression. In this case, is this number in the concept? And if it is, it's a 1, and if it's not, then it's a 0. So you can see that if we if we have a yn that's not in our hypothesis, this thing is 0, and since we're multiplying a bunch of things together, the whole probability or the whole likelihood will be 0. Whereas if this is true, then this is 1, which means it just goes away. Now the probability, now assuming that yn is in our hypothesis, the probability that we see that specific yn is 1 over the size of h. So we can simplify that a bit. Remember I said that for each d has to be within h. If it's not, we can give a probability of 0 to the whole thing. So we can kind of pull out this indicator function. Note that I'm not putting a specific yn, but all of our data, and asking, is all of our data within h? If it is, then we're good. If not, then this whole probability is going to be 0. By the way, this is I think a typo in the textbook. I think this is correct to say that D is a subset of H, not D is inside H, because again, D and H are both sets. Now, what is the probability that we see a given set, assuming that all those numbers are within our hypothesis? It's this thing to the power of n, because we see n numbers. Now, this shows us something useful that helps us formalize part of our intuition. Note that this probability, or this likelihood, is going to be smaller the larger h is. So if we put h as the set of the even numbers, and again, we gave d as 2, 8, 16, 64, there are more even numbers than there are powers of 2. So size of h is going to be larger for the even numbers, meaning this probability is going to be smaller. And both of them are going to have 1 here. So if we look at the likelihood of the even numbers given our hypothesis, that's going to be lower than the probability of the powers of 2 given our hypothesis. So we could imagine one strategy for concept learning be, okay, think of all of the concepts that you can imagine and ask which one gives you the highest likelihood. And that would work here. It would tell you that the powers of 2 are they're a better concept for these numbers than the even numbers. And in fact, we could even put specific values on this. If you actually compute these numbers, you find that the likelihood of h even is about 10 to the minus 7, and the likelihood of h2 is 10 to the minus 4. So you can see that that H2 has a much higher likelihood. Okay, but that's not the whole story, because using just the likelihood, we would think that giving the concept powers of 2 except 32, that is going to give us a better likelihood, because the size of H is going to be smaller. So there must be something else that tells us that the powers of 2 is a better concept. And we have kind of this intuition that powers of 2 are somehow more reasonable than powers of 2 minus 32. Okay, how do we formalize this fact that we think of some concepts as being much more reasonable than others? Again, the powers of 2 are much more reasonable than the powers of 2 minus 32. Well, we imagine that we come to the problem with some prior knowledge about the problem, that is some prior distribution P of H. Notice that I've written here P of H, not given anything in particular, that is not given our data. And that prior probably looks something like this. We probably put some high probability on H2 and H even, that is the powers of 2 in the even numbers, because we think of those as kind of reasonable concepts. And we might also put a high probability on some other hypothesis, like that we see the prime numbers, but the powers of 2 minus 32, we don't think is very reasonable, and so we don't put a lot of prior probability on it. Now, if we were to come up with a realistic prior for what a human might have as their sort of prior idea for what's a reasonable concept for this problem, it might look something like this, where we have some high prior for some concepts like even and odd that are kind of the first concepts we think of when we think about numbers, and then some sort of probably roughly equal prior for a bunch of other reasonable rules like the powers of 2, depending on what the number ends in, if the numbers are squared, or maybe all the numbers combined, and then some much lower prior, perhaps a prior of 0 for these kind of really weird rules like the powers of 2 minus 32 or the powers of 2 plus 37. You might also add to this some distribution over the possible intervals, that is, the numbers between 20 and 30, or between 28 and 42. Those also seem like reasonable rules, so you might add that to the prior here. But let's get back to the question that we really want the answer to, which is how do we learn a concept from data? That is, what we really want is what's the probability of a given concept given the data we view? And we can figure that out just by multiplying together the prior, P of H, times P of D given H, which recall is the likelihood of H. Now notice if we wanted to write this whole thing, we would have to put P of D at the bottom. But often we're just trying to compare different concepts or different hypotheses. So often we don't care about the denominator, and instead what we use is just the numerator and use the proportional to instead of the equals. So that is, this is proportional to this, that is, it equals, the left side equals the right side times some constant factor. In this case, constant, because we've already observed those values. Okay, so let's look at a specific example. So let's start with the example of when our data is just the set 16, that is, we just see 16. So again, I'm showing you here our prior distribution over all of these rules on the bottom. Then we have our likelihood, that is, what is the probability of the data, in this case just 16, given all those rules. So note that some of the rules are impossible. So it's impossible that the rule is the odd rule because we've seen an even number. So we get a likelihood of 0 here. The highest likelihood rules are the ones that are very small, but also match our data. For example, the powers of 4. You can see that all has a non-zero, but very small likelihood, because again, all is the set of all numbers, so that's a very low probability of seeing D, and so a low likelihood for all. And so you can see we did that for all the different rules. Now we can see what our posterior is. Our posterior is the probability of as our likelihood times our prior. So you can see some of these rules that we're not willing to consider, like that are 0 in our prior, they might have high likelihood, but that doesn't matter. They still get 0 for a posterior. And you can see, other than that, a bunch of rules show up as with high probability in our posterior. The one that gets the biggest boost is even, because you can see that we have a very large prior on it. So even though the likelihood might not be so high, it gets a pretty high posterior. But also notice that our posterior is quite diffuse. That is, because we don't have very much data, we don't have that much knowledge about what our posterior is, or rather what the concept is. So our posterior is diffuse. It has a lot of different rules that have non-zero probability. Now, let's look at the example we've been working with, where our data is this powers of 2 set, 2, 8, 16, 64. So our prior is the same, because again, of course, our prior doesn't get to depend on what data we see. If we look at the likelihood, we see that many rules have been ruled out. For example, odd, multiples of 3, and so on. All of those concepts are impossible. You can also see that a rule like all ends up with quite low likelihood, because that probability of seeing each one of these numbers, 1 over 100, we get that 4 times here. So it's 1 over 100 to the 4th power, rather than in the last slide where it was just to the single power. Now, once we see our posterior, then one more thing to note in the likelihood is that the likelihood, again, of powers of 2 minus 32 is actually higher than the powers of 2 itself. Now, once we see our posterior, we see that we get overwhelming probability, very close to 1, on the powers of 2, which matches very well what we do as a human. Once we saw these 4 numbers, the powers of 2, these 4 examples of powers of 2, we would have a pretty good idea that the concept we were trying to learn is the powers of 2.